All right. Hello. Can everyone hear me? Let's see. Let's get some camera going. Okay. Camera. You go above. There we go. That's a bit bright. Okay. Yeah, let's just do that. All right. So, welcome to the sort of implementing Kalman filters in a practical way tutorial. So, I'm not an expert on these. If you want an expert, there's other people probably in the Discord channel that can help you out more than I can, but I feel like what will be valuable to you in this tutorial is the C++ code, or just to see how it's implemented in C++, and just sort of the basic ideas of sort of the feeling of a Kalman filter, like the feeling of how it works and the intuition, and implementing it practically, at least on an Arduino. Because I don't know, I haven't seen in the Discord channel anyone like saying like, oh, here's my code for a Kalman filter, and then being like, this will work. This is how it looks like. I mean, there might be. I haven't searched, but from what I've looked at, I don't think many people do that. And so I thought that this would be a good chance to do that. So, yeah, disclaimer: I'm not an expert on this stuff, and probably like I'm not really going to like derive every single part of the Kalman filter. Like I'm not gonna like don't expect to know like, oh, why does this matrix get multiplied by another matrix here? Most like especially for like the update steps of the Kalman filter, it kind of goes over my head. But it doesn't matter, at least for the purposes of this. But I will show you, exactly what equations that you need to use and sort of the intuition of how it works. Okay, so cool. Okay, so let's start with an example. So today we're going to be like in MATLAB, or it's not MATLAB, in C++ for the Arduino. Today we're going to be making a Kalman filter to track the altitude of a rocket. So so we're going to be, to track the altitude of the rocket, we're going to need, normally use a barometer, right? But a barometer is very noisy, and it can, it's basically very noisy. At least my barometer that I have in my rocket can give me a reading anywhere, probably, it's like plus or minus 0.25 meters in the noise, right? So it can go up and down about half a meter or so, which isn't super great. And sure, you can, hey Carmelic, sure you can, you could filter, just like have like a averaging filter, a moving average filter, but those produce a bit of lag, right? Like which is probably fine for a rocket. But anyways, we like to over-engineer things and over-design things and try to, once you make your rocket, you kind of feel like, okay, like now what can I do? Well, either you try to build it better, you try to make the hardware better, right? Or you try to make the software better. You try to improve, explore the software and see, from the comfort of your code, you can just like try out different things, right? So that's sort of why I went to try to make a Kalman filter for this. You don't need one, at least for altitude, but it does help slightly, and the bulk of it is from the barometer. So so how do we implement, or what are we going to need for this, right? We're going to need measurement readings, right? So we're going to need to read the altitude using the barometer. We're going to need to read the acceleration using the accelerometer, and we're going to need to read the altitude using the GPS. Now the GPS is kind of like a third part of this whole system or whatever that you don't, I don't think you really need it, but if you're doing tracking over a longer period of time, probably, especially if it's like supersonic flight and your barometer goes crazy, a GPS is helpful, and especially if you're going to be tracking horizontal distances, like how much your rocket drifts north, south, east, west, then a GPS is definitely needed, and the barometer in that case won't help you. So let's go over what a Kalman filter kind of does, like the intuition, right? So let me just erase some of this stuff here. So we've got our rocket here on the ground, and this rocket is at, this is 0 meters, right? And when the rocket launches, so let's just see. So let's actually do this. So the Kalman filter is basically, like a normal filter, just filters the measurements, right? It really, you give it the measurements of what your barometer or something tells you, and then you decide on some kind of average between the measurements, sort of, right? But a Kalman filter is ultimately a way of combining multiple sources of information about your state, right? And so the simplest Kalman filter would be, still to use a barometer, but you also use an equation. So this is what's sort of the predict step, right? So a Kalman filter would be, you can sort of think of like the prediction step is sort of like having another measurement sensor in there, right? But the measurement doesn't come from an actual real-world measurement. It's the data that the predict step is giving you just comes from saying, oh, well, I know my state, last time step was this kind of state, right? Like I know what my position was last time step, and I know what my velocity was in the last time step, and I know that if I waited this much time, your time step time, then based on the velocity, my position should now be this, right? And my velocity should now be this. And so it's kind of like, we're kind of like predicting, well, yeah, it's prediction, right? We're predicting where the rocket should be based on previous data. But then the measurement comes in at a time step as well and tries to correct and say, hey, well, actually the data is this. And so actually this is probably better to not do it with this rocket because it's better to visualize it with a like single point rather than like a long rocket, because it's just less confusing. So let's say we have this rocket, but we're going to say that the bottom of this rocket here is where our instrumentation is, right? So at the bottom of the rocket, that's where our instrumentation is, and right now it's reading 0, right? So I'm going to move the rocket out over here, and we're going to model this as just, or show a little thing as just like a point, right? So this is our point right here. Let's just do maybe this. This is our point right here, right? So our rocket is now at 0, right? And we're going to wait a certain amount of time, so we know it's at 0, right? So our state, which would be represented by like a vector, would be, let's say the vector is position, velocity, and acceleration, right? And so our position would be 0, velocity is 0, our acceleration, let's say like right now the acceleration felt is like, 1, right? 1 meter per second squared. And so that's sort of the state right now. So then what we do is we wait a time step, right? Like let's say we wait half a second, right? And we know based on the acceleration from before and the velocity and position from before, waiting half a time step will give us, let's say the rocket, so let's say the waiting half a time step will give us a still acceleration of 1. Let's say it gives us a velocity of, now 0.5. Don't worry about the math, but basically the math is based on the the acceleration, right? So based on how much you were accelerating, actually let's do that. So let's say we know that velocity, so we say acceleration is the same. We say we know that velocity equals the previous velocity, so let's say vi equals vi minus 1, and then plus 1/2 at squared, right? Or let's just say this is capital A t squared, right? And so in this case, it would be, let's say our time step was 1/2 a second, or let's just make it easy. Let's say our time step was a second, right? So we say that equals 0 here. We say plus 1/2 times 1, whoops, and then times 1 squared. Well, come on, there, squared. So that's basically 1 and 1/2, that's 0.5. So our vi equals 0.5, or yeah, our v velocity at this time step is 0.5. And our position is equal to, our position is equal to, we know position equals position before, right? So position I equals position I minus 1 plus the velocity before times t, so v I minus 1 times t, and then plus 1/2 at whoops, sorry, wrong. This is bad. So this isn't 1/2 at squared. This is just at, right? So this would be just a times t, so 1 times 1, and so the velocity is 1. There we go. Okay. So now we have our velocity is 1, and then here in position, we basically have plus this, and then plus 1/2 at squared. And if you sort of do that, you get 0, because we started at 0 here, right? Because this is our pi minus 1. This is before. Plus 0 here, because our velocity is 0, and then plus, oh, why did I do this? Why is there a 1 here? There. And then plus 1/2 at squared. That would just be 0.5, right? So plus 0.5. And so there's our new position. And so now we say, okay, this is our prediction step, right? What we just did is predict. We didn't make any measurements. We just said, okay, well, what were we at before? And assuming that what's happening before is still happening, now where are we at, right? Assuming that acceleration is, happened over this time step, now what are the velocity and positions? And then we basically say, okay, so now we're saying, well, now the rocket is here, right? So now the rocket is, this is 0.5 position, right? The rocket is here. But one thing, so that's our prediction step. The prediction in blue told us that the velocity is here. But at the same time, let's say we get a measurement, right? And our measurement, the barometer, so let's say baro, says that the position is actually 0.75. And so so we can show, okay, well, the position for the barometer says it's right here. So now the prediction is a blue, the red is a barometer, and we need to know, well, how much do we trust the barometer and how much do we trust the prediction, right? And it's sort of, think about it as like, let's zoom in on this, and this is sort of ultimately what the Kalman does. The Kalman filter basically figures out how much to trust the measurement and how much to trust the prediction, and it tries to pick a value in between the two. But how close do you get to the measurement and how close do you get to the prediction? So if you do all this in the Kalman filter, and the Kalman filter says, oh, well, actually, I'm estimating the position here, that means you trust the measurements more than the prediction at that time. If you say, well, I actually think the position is here, that means you're trusting the prediction more than the measurement at this time. If the Kalman filter says my estimate is here, then it trusts both sort of equally, right? And this is sort of the whole part of the Kalman filter, is how do you actually find what to trust more, right? And I'm not going to go into like the math of it too much. It's kind of like each time you make a prediction, there's kind of like, think of it like error bars around it, right? So let's say like the prediction can be anywhere between here and here, right? And each time you make a measurement, there's error bars around that too. And so I'm just going to make these in red. So they're there, and let's say there's the error bars, right? And the Kalman filter, think of it as basically it would, based on the error bars, and these error bars change each iteration. And based on these error bars, the Kalman filter will pick something that where both of these bars are sort of overlapping, which would be in this sort of section, right? So it would be somewhere here. And so the Kalman filter would say, oh, okay, well, that's the next position. And then what would happen is, that's your estimate, right? So that would be your estimate. And what you would do is now you would wait another, so now you would plug that estimate into, your state. That would be your new state. And next time you do the prediction step, you're gonna base it off of this estimate, right? You're not gonna base it off of this old prediction here. You're gonna base it off of this estimate. And then you predict again, right? So you now predict, and your prediction says, okay, well now as we're rising more, based on the velocity and the position and acceleration at this point, we, with our prediction, we think that after a certain time, it's going to be up here. And that would be your prediction. And then what happens is you do another measurement, and your measurement says, well, now I think it's down here. And so then what happens is both of these also have error bars here, right? And so these would have error bars, and then it would pick sort of a point in between those two error bars. And it basically, the part about the Kalman filter that is, I guess, the complicated stuff is how these error bars change each iteration. How do you how do those get figured out and calculated, and then how do you get the Kalman filter to choose in between these, right? And so we're not going to be going too much into how the error bars work, because there's a lot of matrix stuff, and it's well, you'll see the equations, and I can't really explain much on how the equations exactly work and intuitively tell you, I guess, but I can definitely talk about the prediction equation, and then I'll show you in C++ how to implement everything. So don't worry. I don't understand the update equations as much, but I know them, and you'll see them in C++ as well. So let's just go through. Let's delete all this. Oh my God, why does it decide not to erase that? Come on. Okay, so let's just take that out. Okay, well, can I lasso this? And there we go, delete. Okay, so what we're going to do is so let's just go through a prediction step, right? Or what do you need for a predict step? Well, let's go prediction, predict. And this is how it sort of works, is you have a state, right? So you have a previous state, right? And your state, think about a state as just well, what's your rocket doing, right? What are the variables or the properties of your rocket or of the rocket flight? What is the data of your rocket that you're interested in, right? And in this case, we're interested in altitude, right? So that's a position. We're interested in velocity, and we're interested in acceleration. And so in this case, let's consider only a Kalman filter with only a barometer. Let's say a Kalman filter with only a barometer, right? So let's not say there's any accelerometer in here. And so let's say our barometer is the bias is removed, right? So let's say we have the barometer, when it's on the ground, it's reading 0, and there's no bias and stuff. So, and we're interested in what? We're interested in position and velocity. Actually, I think, let me think about this. I think velocity, well, let's just do it. Let's just do this with the accelerometer as well, okay? So we'll do this so we're basically looking at position, velocity, and acceleration. So our state is going to be this. We're going to say, well, our state is position, let's call it P, yeah, velocity, and acceleration, right? And this is what's called our x matrix, right? So you're going to see this in the code, and this is the x matrix, or x vector, right? And this is x at the current time, right? So xi. And we're going to, and what does that equal? Well, remember how we said position equals position, or let's say position I equals position of I minus 1 plus velocity of I minus 1 times delta t plus 1/2 a of I minus 1 t squared, or delta t squared. Let's see, delta t squared. So remember we saw that. So there's that. So we have an equation for position. Now let's look at an equation for velocity. So we can say, so remember vi equals the previous velocity, and then plus 1/2, or not 1/2, sorry, plus ai minus 1 delta t. Okay? And in this case as well, we're going to say, let's say this is a constant acceleration thing. I'll show you later, well, we'll talk about later how to not worry about that as much. But anyway, so we're going to say a equals ai equals ai minus 1, right? So it's just constant. The acceleration doesn't change between time steps. And so this is basically our prediction equation, right? So we just need to put this into matrix form. So the way we do that is we basically, let's just zoom out a little bit. There we go. So the way we do that is we have we need to make this matrix, or we need to make this equation in this kind of form. So I'll show you. So the form should be x, whatever the x, the current time step is, times an F matrix, times the x matrix of the previous time step, so minus I minus 1, and then in this case we're just going to keep it like this. But if you do have like an input, like a known input, then you would have something like times b, and I think it's ui minus 1, I think, something like that. So, but basically what this is you'll see. So the x, remember how the x matrix, or the x vector, is just PVA. That's the same style, like the same form that xi minus 1 will have, right? It'll also have p, v, and a. But it'll have the position, velocity, acceleration of the previous time step. And so we need to multiply, we need to make this multiplication here so that we get this new time step. And so these equations on the left here are exactly sort of what we need. Give me a second. Whoops. Nope. Okay. Yeah, so these equations on the left here are exactly what we need. So let's, we're going to write them out, and there's a bunch of stuff that'll turn into this F matrix. So the F matrix is a 3x3 matrix. So this is our F matrix. And the F matrix is the sort of size of the matrix is just the size of your, it's a square matrix, that's the size of your state vector, right? So if we have a state vector of 3, let's say, what is it, rows times columns, 3 by 1, then the F matrix is a 3 by 3. And this gets multiplied by an x, I'm doing this like bold just to show these are matrices, an xi minus 1 matrix. And we can talk about ui minus 1 afterwards. We don't need it for this example. And so, yeah, so we just need to find, okay, well, what do we put in this F matrix? Because we know that here, this is just p I minus 1, v I minus 1, and a I minus 1. And when I say I minus 1, I mean, what is the position, velocity, acceleration at the previous time step, right? So if our time step's 10 milliseconds, what were the states 10 milliseconds ago? And based on what they were 10 milliseconds ago, what are they now, right? And so we just need to basically take this equation on the left down here and put it in the form of a matrix here, right? So in this case, let's look at position. And remember how matrices work. So, well, I'll write out the top term and you'll see sort of how it works. So we're going to say, so we know that pi so there's this pi minus 1 term here that gets added, so we're going to say that's a 1. It's just being multiplied by 1 here, if you think about, yeah, it's being multiplied by 1. Here, what is vi minus 1 being multiplied by? Well, just delta t. So we're going to say delta t. And then here, ai minus 1 is multiplied by delta t squared divided by 2, right? So we're going to say delta t squared divided by 2. And so let's just look at, okay, well, for those unfamiliar with matrix multiplication, basically this is what we're doing is we're saying pi minus 1 multiplied by 1 plus vi minus 1 multiplied by delta t plus ai minus 1 multiplied by delta t squared over 2. And that's exactly what you see here. Whoa. Yeah, here. And that equals p, right? So sort of think about this, think about that multiplication as just like taking this matrix, this vector here, and sort of flipping it horizontally. So now you have pi minus 1, vi minus 1, and ai minus 1, and you're multiplying these terms and then adding them together. Okay? And so now let's look at how do we get the next matrix, right? So the next one is starts with vi minus 1. There is no pi minus 1, so the pi minus 1 does not influence velocity. So we're going to say, well, that's 0 here. We're multiplying that by 0. And now, what about vi minus 1? Well, that is, we're just saying vi minus 1 in this case is 1, right? It's just staying the same. So we're just going to say 1 is multiplying by 1. And then ai minus 1 is just multiplied by delta t. Okay? And then down here we say, well, acceleration on the bottom left here is just equal to the same acceleration as before, and the position and velocity do not influence it, right? So we're going to say, well, that's 0, because position is multiplied by 0, velocity is multiplied by 0, and then ai minus 1 is the same, it's constant, so it's just 1 here, right? So this is our F matrix. So this is our sort of second most important matrix here, right? The first most important is the state matrix or state vector, and F is the second most important matrix here. So that'll be really important in the code later. So this is basically our predict step, right? Like what we're going to be doing is we're just every time we want to predict the position, at maybe do this every 10 milliseconds, do it every 5 milliseconds, whatever. Every time we do that, we're going to be taking the old state, multiplying it by this matrix here, and getting the new state. And then the new state will become the old state in the next predict step. Okay, so that is all that you need to do that is most of what you need to do in the predict step. So now let's let's do this then. Let me just find code. Let me just look at, this is the code for the Kalman filter here that I have. I will post this up probably on GitHub, and I'll have a link link to it in the description. So what we're going to do is, you see here I have a function called predict, right? So this is let's make this bigger, come on. So I have a function here called predict. And all this is doing at the top here is, you can kind of ignore this. This is, finding out what is the time, right, between predictions. This is just a time thing. And, you can ignore this. This is just looking at, just not counting the first time step. But this is the predict step, is we're creating this F matrix, and really this F matrix, we're creating this F matrix, and the delta t is different each time, so we have to make this each time. And you can sort of see here what's happening. We're saying, hey, there's 1, there's delta t, there's 0.5 times delta t squared, and then the same thing here for velocity and acceleration. So this is our this is exactly our F matrix from before. Then what we're doing is we're saying, hey, look what we're doing here. We're saying the next state is equal to F times the previous state, right? And this is actually a matrix, like you might not be familiar with this form, because this, we're doing a matrix multiplication here, but you can't do that natively with the Arduino. So there's this library that I'm using in the H file. It's called Basic Linear Algebra. And this library is really great. Like, you could probably, I don't know, maybe could make a faster one by yourself, but this kind of lets you specify the size of matrices. So let's say, like, for my X matrix, you can see here I'm specifying a 3 by 1 matrix, and I'm setting it to 0, 0, 0 here. But anyway, so that, and then you can like set your matrices to be like, you know, just like this. And anyway, so yeah, so here we're just saying, hey, our old state, or our new state, position, velocity, acceleration, is our old state times this F matrix. And the F matrix, I think it's called the state transition matrix. It's just how does your state change from what it was before to what it is now, right? And it changes based on these values here. What you see down here is a little bit more, let's say, harder to understand. But basically, this is where like the P term comes in, right? So in the predict step, let's go back to here. So in the predict step, you need to know, let's see. Yes, yeah, the library is really good. It's a really, really clean and simple and works really well. Yeah, so basically the predict step, not only have to find out what is the X value, like what is the state, we also have to sort of find out what I talked about earlier, where it's like, what are the error bars, right? Like, yeah, like what are the error bars of this prediction? How much, what is sort of the now maximum, minimum, and sort of value of the error bars of this prediction? Like, how sure are we of this prediction? I know that's not like the exact definition of this, and but it's sort of the way I think about it, and you can sort of dive deeper into this later on. But so we found the state here. So in a predict step, we find the state, but we also need to find what's called the P. So this is kind of, so it's not the same as this position here. We can call this POS or whatever, right? Position. But the P matrix is a matrix, it's a covariance matrix, right? So this is just a matrix that is a 3 by 3 matrix. Let's just say, you know, how do I, so let's say it's a 3 by 3 matrix, right? So we'll just say it's a 3 by 3 matrix. It's the same size as your F matrix here. And the P matrix, it basically, think about it as just like, this is the matrix that holds the error bars of the prediction for the position, velocity, acceleration, and how they sort of interact with each other as well. And we need to update, the P matrix also needs to be updated, right? So there's a P matrix at the current time step, and that equals the P matrix at the previous time step multiplied by a few things, right? And what it's multiplied by, let's go back here, and what it's multiplied by is your F matrix. So here you can see the P matrix is multiplied by the previous matrix, or sorry, it's a function of the previous matrix, your F matrix that you have here, and then plus a Q matrix. So yeah, so you've seen these already, right? But what is the Q matrix? So the Q matrix is also another 3 by 3 matrix, but it's sort of what you, it's sort of like it's your noise. I think it's like your process noise covariance matrix. I think that's what it's called. And so that's another matrix right there, right? Q, and it's also 3 by 3. And what that matrix does is you set the values of the Q matrix at the beginning. So the Q matrix stays constant. The values don't change. But what you do is you set the values to sort of your covariances of your process. It's basically your process noise. It's kind of like, how well do you trust your process, or how confident are you that your process is correct? And what I mean by process is this, right? How confident are you that these equations here, let's say these equations here, are actually what are happening to your, let's say, rocket, right? And this will actually come in, especially for this acceleration term, so this part here, because we know that the acceleration of the rocket is not actually constant, right? The acceleration is not constant. It goes from starting at 0, your engine starts to fire, it starts to go up, and then your thrust starts to sort of, average out at, well, settle down at a certain constant value, and then it goes back down to 0. So this acceleration is definitely not constant, but our prediction, our equation, is assuming it is. And so what we need to say to fix this, and sort of what we need to say to fix this is say, well, we're not very trustworthy of this section here, right? We're not very trustworthy of the acceleration, being constant, right? We don't really know that the acceleration. We don't really know the exact acceleration, at least at this point here. Like that'll come in the update equations, but we're very sure that it's not constant, but this is all we have right now. So if we're very sure it's not constant, and we don't trust that process, if we don't trust the process equations very much, you would put larger values basically in this matrix, right? So the larger the value, the less sort of you trust the process to give you the correct values. And this could also happen because there's things that you just don't measure, don't account for, like wind, and air, drag and things like that. And rather than trying to model the wind and the drag, which could give you more accurate answers, you could just say, well, how about I just expand the error bars on this prediction, right? I say it might be good enough to just say, well, I'm not very trustworthy with this equation. I'll trust the measurements a bit more in this case. But so sort of this matrix is usually a diagonal matrix, and what you would do is say, okay, well, if I don't trust my position very much, let's say this value is a 10 here, right? And then here it'll be 0, 0 here. So it's a diagonal matrix, and on the diagonal are how much noise do you think there's going to be in your position, velocity, acceleration. So in my velocity, I could say, hey, my velocity is also 10, and also my acceleration is 10. And so this would look sort of like this. And this is actually how much variation do you think there's going to be in each of these terms, but within the next time step, right? So these should be scaled based on your time step. So if your time step is very short, you don't actually think that in 10 milliseconds your rocket's going to be, at this value. Like let's say you probably would want to make this value smaller, because in a short time step you're more sure that it's maybe not within 10 meters. This isn't exactly saying, hey, this is within 10 meters. It's a little bit more involved than that. You sort of find the variance, and then you do the math for that. I'm not going to go over that too much, but basically the higher the numbers here, what you need to know is the higher the numbers you use here, the less you trust the equations down here, right? The less you trust the process equations, and the more you'll. So what I would do for this acceleration is probably for the position. Oh, that doesn't delete. Okay, come on. Let me select this. Okay, delete that. Come on. Okay. And so what I would do is for this acceleration is I'm pretty sure that the position is going to follow those equations. So, let's say it's 0.01, and let's say the velocity is, even 0.001. The velocity will follow the acceleration, but the acceleration here, I don't think it's going to be constant, right? And so I would say, I would put this as like a much higher number. And this is sort of where tuning the Kalman filter comes into play, is finding these numbers that you need, and just seeing what the Kalman filter gives out in your graphs and stuff. And so this is, so that's really all this is just how much noise you think there is in the prediction itself. Not in your sensors, but in the prediction in these equations, and how much you trust those equations. And you can see here, we're just using this Q to update this process covariance matrix basically here, this P matrix. And that's all it is. That's all you do for the predict step, right? Is you just find out your state, and you find out how much you trust that state, basically, right? And this is all without using any measurements. Oh, let's see. Steve Atto is asking, the acceleration is from an accelerometer or simulated? No, so the acceleration would be from an accelerometer. But at this moment, we're not looking at, we're not like measuring anything yet. We're just predicting we're predicting what's the next acceleration based on our previous acceleration. And in this case, we don't have an equation for really what is our next acceleration based on our previous one, and we're just assuming it's constant, even though we know that's not the case. I'll show you how to do that with like the B and UK matrix. You can do that as well afterwards. But yeah, the acceleration is assumed constant in this case. Nathan's saying, is it appropriate to account for a changing dt in this and do like 5 dt in Q matrix? Actually, I think, yeah. So if you want this to be even more accurate, you would probably like change the Q matrix in here each time. So you would have like your constants for the noise, but then they would be scaled by your dt, and so you would have like a Q matrix here that has the dt in here as well. Okay, so let's look at, so we got the Q matrix, we got the P matrix, we got X, and that is all you need, right? Like the, you now have where was your rocket before, and where is it now, right? And how much do we trust it? If we continue just doing prediction steps, if we don't look at measuring anything, if we don't look at updating anything, we're just doing the prediction step, and we just keep doing this every 10 milliseconds. What's going to happen is this X value here, the state, is going to become more and more inaccurate, right? We're going to be less and less sure that this is the right state, right? Because we know there's noise, we know that the acceleration isn't actually constant, and there's uncertainty a lot. There's a lot of uncertainty in this prediction. Even it's a very, very clean equation, right? It doesn't model a lot of things that are happening in real life, and so if you just kept predicting using the prediction step, this state would diverge to something that is not even the correct state. And this P matrix would just like get larger and larger, right? The values of this P matrix would get larger and larger, and the Kalman filter would be like, well, I'm getting even more and more unsure of where I am. And so we need a way to basically so this is where like the update equation comes. So we need a way to get the Kalman filter to say, okay, well, we've predicted this many steps, and I'm kind of I feel like I'm in this location, and I'm not very sure about it. And then this is where the update comes in, where you take a measurement at this point and you say, oh, well, you thought you were here, and you thought you were, or let's say you thought you were in the middle here or anywhere in this circle, and the update equation comes in and says, well, I think I'm actually somewhere here in this circle, and this is my certainty. And then the Kalman filter sort of takes a happy medium sort of between the two. And so this is where the update equation comes in. And so the update equation is, let's do this. So I'm going to write these out just in, actually, you know what? I'm going to show you just a blog that has this stuff, because it's written out way better than what I could write. Let me just see. Yeah, so this is a really, why isn't it not showing? There we go. Okay, so this is a really good resource here. This is how I learned how a Kalman filter works in pictures by Bizarg, and the link is up here. You can just write this in Google or something. I'll probably put in the description. And really, if we go down to, let's see. So if we go down to here, this is a bunch of matrix math here. But there's just like, yeah, but the only important thing that we care about is, well, how do you do the update step, right? And so the update step, to what we need to do is we need to say, well, we have this measurement, but we need to say, well, based on this measurement, what is the position, velocity, acceleration? How does that influence it? And how does how sure are we, and how do we choose this happy medium between the prediction and the update step, right? And the K matrix, which is the Kalman gain matrix, is the thing that tells us how much do you trust the measurement and how much do you trust the prediction. And so let's look at, actually, there's another tutorial here. So there's another good website here. It's actually called kalmanfilter.net. And if we look at something around here, and we go to they don't have this. Do they have this all in one summary? Yeah, so this is sort of the summary of what we need to do. So we remember how we had our X matrix here. So we had our state equals F times our state before, and plus this GU, which I'll talk about later, which in our case was like BU. And then here's our P matrix, that is basically a function of our old P matrix times F, and F transpose, and then plus Q, so we've looked at that. Next is the state update, right? So here what we're doing is we're saying, what we're doing is like this matrix is also, you can see here how we're saying, hey, this is also the state, right? So we're saying, what is the state, like we're getting a state from here, but we're also getting a state from the prediction. So this is actually the state based on our measurement, right? So our state based on our measurement is equal to the state before plus this term here. So this is a lot of the calculations you're doing is like further down here is really just to find out what is this what is this K matrix here. And so what this is doing is saying, okay, well, the difference, this is the difference between, like Zn is our measurement, right? So Zn is like, what does your barometer say you're at, right? And this H here and Xn, think about this H times X times state matrix times X as like, what is the prediction saying the measurement should be, right? So this is kind of like, okay, X is our prediction where we are, but this H matrix is like saying, well, our position, the H is kind of just like, how do you convert your state space into your measurement space? So we'll look into that soon, but basically this is saying, you know, what does the barometer say we're at? Like, what does the barometer measure? And minus, what does the prediction say we should be measuring, right? What does the prediction say? What did we predict we should measure at this time versus what did we actually measure? And then you take the difference between the two, you multiply it by this Kalman gain, and then you add it to the prediction of where we thought what we thought we were. And the higher the Kalman gain here, the more we trust the measurement, right? Because think about if this measurement here is, let's say we're at 100 meters, but our prediction says we're at 0 meters. The difference is 100 meters. If this Kalman gain here is 1, in this case, well, think about this as like one-dimensional, right? So if this Kalman gain was just one number and the number was 1, then it would trust this measurement a lot. So it would say, hey, well, we're saying 1 times 100, and we're adding the 100 to the previous prediction. If this Kalman gain were 0, we're saying, well, we're not trusting the measurement at all, and we're only looking at the previous prediction here. And so the next equations down here are really just about how do you find this Kalman gain, right? And when we find the Kalman gain, we also need to find the new P matrix, right? Because remember, we predicted a state up here, right? So at the top here we predicted a state based on the previous state, and here we predicted a covariance, this P matrix, based on the previous covariance. But down here, once we actually take a measurement, we're gonna now find out, well, based on the measurement here, based on the measurement and this Kalman gain, what is the new updated or estimated state? And also, based on the measurement and the Kalman gain and all, well, based on the Kalman gain here and a bunch of other stuff, what do we think is the new covariance matrix, the new P, right? So this P matrix gets updated as well. So your P matrix it's predicting, like your prediction step keeps predicting what this should be based on the previous one, but then new information comes in in the form of a measurement, and you get a better estimate of this P matrix here. And this P matrix is really, think about it again as just like error bars, right? You know, with if you update your P matrix with a measurement every so often, the error bars get smaller, basically, right? Or the error bars change. and this isn't, so let's just look at a few of these matrices, right? So we have the Kalman gain, which basically these equations need, right? So these equations, this equation here needs a Kalman gain, and then this equation here also needs a Kalman gain in multiple places, right? And even like, the transpose of that Kalman gain. And then here, this tells you, well, how do you get the Kalman gain, right? So let's start off with that first, right? So how do you get the Kalman gain? You basically take the previous P matrix, right, which we've done in the prediction step, and you multiply it by this H matrix, the transpose of it, and you multiply all that by the inverse of like this stuff here. And so you have this H matrix again, this P matrix again, this H matrix, and this R matrix. Okay, so let's, we know what the P matrix is, right? We've looked at that before. But what is the H matrix and the R matrix, right? Those are two new things. So you can see down here, this is what the H matrix is doing, sort of, right? You could see, well, we're taking a measurement, right? So, or like we have a measurement, Z, our Z matrix here, and that is related to the state, X, by this H matrix. And so let's look at that here. So if we have a, let's see, if we have a barometer, so we say Z, let's go, we say Z, Z is our measurement, right? So Z is, if a barometer measures 100 meters, Z is 100 meters. So we're going to say Z barometer, baro. And we're going to say Z baro equals some number. Actually, it's probably easier to think of it like this. Think of it as like, we have our state matrix, right? So PVA. And that equals something, I think it would be like this, 3 by 1, sorry, 1 by 3, 1 by 3 times 1 by 1, that wouldn't work, no. So it would be like this, I think, right? Yeah, so basically that equals, let's say, Z barometer, baro. So we basically, we want, this is like our H matrix, kind of, like this is kind of the inverse of our H matrix, but think about this as like, well, if right now our measurement looks at position, right? Our measurement is saying, our barometer saying, hey, we're at 100 meters, that's a measurement of position. And so, in this case, we would say, well, how does the Z barometer measurement relate to each of these three things, right? And we say, well, that is a 1 here, here it's a 0, and here it's a 0, right? Because the barometer doesn't tell us anything about velocity or acceleration. It just tells us about position at that point in time. But we don't want it in this form. So we're not, with the Kalman filter, we're not actually converting the measurement into a state. We're actually, for the purposes of the equations of the Kalman filter, we're actually converting the state, the predicted state that we thought we were at, into the measurement we thought we're going to be at. So we actually would write this differently. We would write it like this, more like. So we have this Z barometer, this is one number, equals some, let's see, equals our state. Let me just see how I do this again. Let's see. I had a thing here. So this H matrix is, equals this H matrix times our state, right? So actually, I sometimes get confused about the size of matrices and when you multiply them, what size they become. So basically we have this H matrix times, so we have this H matrix that will times our X matrix, right? And that will convert our state, our PVA values, into what we think the measurement should be. And so we want to say, okay, well, we have this X matrix, PVA. This is what we predicted from the last time step. And we're going to say, well, what are we multiplying it by, right? So we want to multiply it by, so this is a 3 by 1 matrix. And we want to multiply by a 1 by 3 matrix, right? To get a 1 by 1 here, because this is 1 by 1 here. So I might actually, let's say, move that here. We want to multiply by a 1 by 3 matrix here. So in this case, what we say, okay, well, how does position relate to the barometer position? Well, it's the same, right? So we're saying the barometer position is the position that we're looking at. So it's 1. What about velocity? Well, velocity isn't accounted for in the barometer, so we're saying 0, and acceleration also isn't accounted for there, so we're saying it's 0. So this is our H matrix here, and that's really it. It's as simple as that, our H matrix. So let's leave that for now. So then we're going to look at our R matrix. And our R matrix is the same size as your measurement matrix, right? So it's the same size, 1 by 1, as your measurement matrix. And the R matrix, or your R matrix, is basically the noise of your sensor, right? Like your covariance of your the covariance of your sensor, or in this case just the variance of the sensor. And this you can like measure to by putting your barometer on a table and not moving it, and and then seeing what is the variance of all its measurements. And so this is really just like this is a constant number that's always going to be the same, and this is basically you at the beginning telling the filter, hey, like I trust this measurement this much, right? And so this would be your variance, and I think it's just denoted by sigma or something like that. And it's basically like, hey, I trust this measurement this much, and it could be 0.1, it can be 10, it can be whatever you measure as your variance, and it's just one number in this case, right? It's just the measurement, the variance of your barometer. The higher it is, the less you trust it, right? And so if we go back to our Kalman filter equations here, we've talked about H and we've talked about R. So now we can find the Kalman gain, right? So we have the P like we had before, we've talked about. We have the H now. We have the H here, and then we have our R here. And so we have all the matrices we need to find the Kalman gain. So if we look at the code, go up here, you can see here what I'm doing is what happens is, here's like a function for, so let's do a barometer here. So here's a function for the barometer. So the barometer, what happens is every time the barometer has a new altitude measurement, right? Every time it gets a new measurement, I call update barometer with the altitude. And what I first do is I predict, right? So I basically get the latest sort of predicted state, right? So I just call this predict function, get the latest predicted state based on the previous one. And so now I have like my latest known state and my latest known P matrix. And I take the altitude and I put that into a 1 by 1 matrix called Z barometer, right? And this is where I calculate the Kalman gain, right? So for the barometer. So you see I have the P matrix from before, from my predict step. I have this H matrix, and if I go up to the top here to find my H matrix, see, our H barometer matrix is just a 1 by 3 matrix, right? 1, 0, 0. And so down here, okay, so down here is just our H matrix. And if I double click on these, you can see how many times this sort of appears in all these equations. And this, really think about this matrix, or vector in this case, as like, this thing just converts between state, the state sort of space, into measurement space, and vice versa, right? It just it's more evident when like I guess your measurements aren't exactly measurements of the state, but something else. But usually they are. So yeah. So this, and remember this equation, these equations are going to be always the same, right? So one cool thing is that like with this code here, you can go up here and modify, you know, all these matrices and stuff. Just make sure like they're the right sizes, right? You modify all these matrices with the right sizes, and you don't have to change the code afterwards, right? You don't have to change these equations anymore because they're matrix multiplications. So yeah, so we have this H matrix here and these squigglies are the transpose of the matrix. And we have the P matrix again, and here's our R barometer. So if I go up again to the R barometer, you can see here I put it as 10,000. This is an arbitrary number. I was trying things out, but you know, you would put your number here. And this is a 1-by-1 matrix here. And so now, and then we just take the inverse of this inside stuff, and we have our Kalman, whoops, that's the acceleration. We have our Kalman barometer matrix here, okay? Yeah, so basically that's our Kalman gain right there. So that's pretty good. Next is we now have all the variables, all the things we need to find the updated state, right? So the updated position, velocity, acceleration based on the measurement. And so this is where the measurement actually comes in, you know, the Z value right here. So we basically, we take our old X value, our old state, we take our newly calculated Kalman gain, and we take our measured value, right, so our Z barometer, and we take our H value that we had from before, and we have our old state here as well. And that is basically, that updates, and that gives us our new state, right, based on the measurement. So that's cool. And then lastly, this big long equation to update the P matrix. And again, it's not super scary because we already have all of the matrices we need. So one thing is, like, you'll see this I matrix here. It shows up only twice in here. And this I matrix is the identity matrix. So the identity matrix is just a matrix that has ones along the diagonal and zeros everywhere else. And this would be have to be the same size as your P matrix. So if you introduce a new variable into your state, you would have a 4x4 matrix for your P. You'd have a 4x4 for your I. You would have a you would have a 1x or 4x1 for your X matrix, etc. I'll show you how these sort of change, you know, sizes based on how many states and things you have. But yeah, so basically we have this identity matrix. We already have our Kalman, whoops, here it is. We already have our Kalman gain. We have our H. We have our P from before. We have our I again, Kalman gain, H. We have our K. We have our R and our K. So one thing that you'll notice here as well is that like this value here is the same as this value right here, but this one's transposed. And it's kind of cool because like it's applying, think about this as one matrix, right? So what it's kind of doing is we're saying P equals, you know, some kind of like n matrix, right, times the old P times the transpose of that n matrix plus our this Kalman gain, so let's say our K matrix times our R matrix, which is our noise, times the transpose of our K matrix. So it's just really, it's cool because it's just like, it's literally just, it's actually, you can kind of look at it like this, where it's actually just, you know, you're taking the old P and you're basically converting it, I guess, or updating it with this n matrix. And there's like a special thing with matrices where like you multiply on the left side by the matrix and you multiply on the right side by the transpose of the matrix. I'm not exactly sure. I don't really know the terms of how that works and stuff, but this all gets added to this, or this all gets added with your measurement noise with this Kalman gain. And this gain, remember, is just how much do you trust this measurement, right? So the higher this Kalman gain, the higher you're caring about the measurement noise in this case. But anyways, that's sort of just an aside thing. So yeah, so now we've calculated this P matrix. So one important thing though about this equation is that it's It might not be the exact one that you see online. Like it is, I think it is the one that you see here. But in something like, I think this, yeah, on this page, the P matrix here is actually like this equation. Whoops. It's actually this equation here. So I think, so the reason that I'm not using this one is this page here tells you to use this longer equation because it's more stable. So let's take a look. Yeah, see, so it says, it shows you the more elegant or like the more simplified equation here, and it says, warning, this is much more elegant and rememberable. In many cases it performs well. However, even the slightest error in computing the Kalman gain due to round-off can lead to huge computation errors. And basically it's numerically unstable. So this is, even though it's easy and small and good and easy to understand, I guess, it's not recommended because of just round-off errors. So in that case, I usually use this longer equation. It gives you the same result, but there's less, it doesn't have that round-off error problem. This is sort of a good diagram of how the Kalman filter works, like, or the sort of what you do, right? And so let's look back at the update equation, right? So you basically compute the Kalman gain, you update the estimate you update the estimate based on the previous one and the Kalman gain, the measurement, and then you update the uncertainty, the P matrix, right? And then that's it. That's all you do for the update step. And then you go up here to the predict step, and now with your prediction, you find the predicted state and the predicted uncertainty in the next step. One thing here is that you need an initial estimate, right? So at the very beginning, when you first do all this stuff, you need to know, well, remember how all these equations, or a lot of the equations, rely on knowing what is the state beforehand, right? Like what is the state in the previous time step? And so at the very beginning when you start, you need to know what is the state at the previous time step. You need to just set it as an initial value, right? So let's just go into here, the code, and you can see here I'm setting, I have this function here called 0 Kalman, and all it does is it basically sets the initial values. Maybe it shouldn't be 0 Kalman, this should be like init Kalman, and all it does is it has these initial values here. If we're going to do init Kalman, let's write that here. There we go. Yeah, so basically here is where I put the initial values of x, right? So my position, velocity, acceleration, and the values of my P matrix here. And these are just arbitrary. You would find these out yourself. But this is, so the values of the P matrix here, they're kind of the same as like how you would choose the Q matrix values, but this is more of like how sure are you that the actual states at the beginning are these states that you chose, right? So this is really initially setting this P matrix and saying, how sure am I that this position is actually 0 at the beginning? How sure am I that this thing is actually a velocity of 0 and at an acceleration of 0? And it doesn't, and so this kind of helps because like your initial guesses, they don't have to be very, very accurate. If they're off by a bit, the Kalman filter will slowly converge to the correct values. But the closer these start off at the correct values, the faster it converges, basically. And the more sure you are, so like, think about it like, if you think that the Kalman filter is at 0, 0, 0, but it's nowhere near that, like it's at like 5,000 position, 200 velocity, and 100 acceleration, and if you're very sure about your initial values, but they're actually not correct, it'll take a long time for the Kalman filter to converge to the correct values. But if you have those initial values and they're still way off, but in your P matrix you're saying, oh, I'm not very sure that these initial values are correct. You make these values bigger here, then that will help the Kalman filter converge faster. Because it's not going to sort of stick around and say, oh, like I still think that these initial values are correct. It's sort of think about like the larger the values here, the more the Kalman filter is able to sort of go off and explore what the actual values are, I guess. Anyways, yeah, so that's sort of setting the initial values here. And I mean, that's really most of it. So let's take a look at the acceleration. So the acceleration update, right? Because we're updating every time we get a barometer measurement, but we're also updating every time we get an acceleration measurement. So with that, let's just do this. We say z accel. We need to find, and really when you need a new measurement, like when you're trying to put a new measurement into your Kalman filter, it's really a matter of what is the Z matrix, or usually it's a 1-by-1 matrix. What is the H matrix, and what is the R matrix, right? And that's really it. And so we say Z accel equals some H matrix times this X, right? So our H matrix is again going to be a 1/3, and then our state is going to be, again, remember, P, V, A. And so now, how does our acceleration tie into this measurement, right? So how do these states tie into this measurement of acceleration? Well, the position doesn't matter to the acceleration, right? So that's a 0. The velocity doesn't matter to this measurement acceleration. That's a 0. But the measured acceleration is the acceleration that we're interested in, right? So that's a 1 here. So what we're saying is Z accel basically equals this A here. And so this is our H matrix for the acceleration. So remember how before we had an H matrix for the barometer of 1, 0, 0. Here, for the acceleration, we have 0, 0, 1. If you had something that's tracking the actual velocity, right? So you have like some kind of measurement that is able to tell you velocity, you would then have a H matrix that's 0, 1, 0 in this case. So you can see in the code here, I have this update accel function here as well. And this gets run every time the accelerometer gets a new value. So, or like every time the accelerometer measures a new value. And what we do is at the beginning we predict just to get the next time step. And then we say, we put this accelerometer value, the actual number, into this Z accel matrix. We just make it into a 1-by-1 matrix. And then we just do basically the same equations as we did down here, right? So for the barometer, we did these. We do the same ones that we do here, but we just have different variables for the acceleration, right? So the acceleration H, you can see it pops up in a bunch of places. The R for the acceleration, so the noise that we think the accelerometer has. And we have this the Kalman gain matrix for the acceleration as well. And everything else is the same, like the X is still the same X as before. The P is still the same P as from the other update equation, and that's it. So also one thing I have at the bottom is here this thing called set data variables. This is just for me what I do is I take the values, like the elements in this state matrix, and I put them into my own data variables that get tracked in my sort of Rocket program. This is you can either not use this, or you can decide to fill this out with your own global variables here. I have like a struct that's called data, and then this is where I put them in, so I can like graph them and have put them onto an SD card. So I'm basically looking at the X matrix and the P matrix here. And let's see. So let's go. Let's talk about. Yeah, so let's just talk about the code a little bit more then. So yeah, so I have the CPP file, the source file here of the Kalman filter here, and I have this .h file here, the header file. And the header file just includes the linear algebra library, and it includes my sort of data library that I have for my own Rocket. You don't need this here unless, you don't need this here. You would change this to whatever. But here I have a bunch of the functions that I'm going to use, right? I don't have this as a class, so this is something that you might want to make into like a class, right? So that later you can say, my Kalman, or let's say your class, you would like in your main code or whatever, right? In main.cpp, you would say, somewhere at the top you'd say Kalman equals my Kalman, or whatever, right? And then later in your predict step, wherever you want to predict, you'd say my Kalman dot predict, and then you would just predict. There wouldn't be anything you're adding to it. And then whenever you get measurements, you would say, whenever accelerometer has new measurement, do this. And then we say, so we would say my Kalman, in this case it would be my Kalman.update Excel, right? And we're just going to say, well, my Excel value, accelerometer value. And then you would say, whenever barometer gives new data, do my Kalman dot update baro, and then baro value, right? And and so that's how you sort of feed in the Kalman, right? So that's sort of how you you call this prediction step at some kind of time step. You can do this depending on your processor. You can do this every 5 milliseconds or whatever. And then you can call the update Excel and update baro whenever the values actually come in. And if you want to know, well, what is the actual predicted, like how do I get the actual position and velocity acceleration at that point? It's just a matter of changing this this function here, changing this to give you whatever. Like basically you could include, like here what I have is I'm including this data.h, which just basically gives me this struct that I have that has these variables here. And I'm just saying, okay, well, data.my Kalman x position equals the 0, 0 term in this state, right? So 0, 0, here's 1, 0, and 2, 0. So this is just position, velocity, acceleration. And that's how you it's sort of, in this case, it automatically gets those states, right? So it basically gets the state already and puts into my variables that I need for later on. So I don't need to actually ask for those variables. What you can do is say, make a function that says, float get Kalman position, and then you would do something like, return x 0, 0, something like that, right? And then you would have get Kalman position. You would put this in this, in here, something like that. So obviously this isn't a class right here, right? So this is all just a normal function. So, but if you did have a class, right? If you did say Kalman my Kalman and you made this into a class, you would basically then say, my Kalman dot get position, and you'd say, I could say float my position equals something like that, right? And then that would get the position at the current state, right? So let's see. Any questions right now? Is there anything you guys want me to go over again, or anything anything that you don't understand still, or you're confused about? I don't want to miss anything before we go on to the next part. Okay, so I think the thing is kind of laggy as well, so I'm going to just continue on because there hasn't been any questions so far, for a while. But yeah, if you have any questions, feel free to stop me at any point. Let me just see. Okay, cool, Nathan. Let me just see the Discord. Is there any? There's no questions. Okay, cool. All right, so let's look at another way of doing this. So there's also a GPS here. That might be, I'll add that for an advanced thing soon, but let's look at a different way of getting the accelerometer. So let's say now, so rather than, so remember how at the beginning we said oh, acceleration is constant, right? We said, if we looked at over here, we said, hey, acceleration is, we're predicting that the acceleration is the same acceleration as before. Well, how about we do one better? How about we say the acceleration is actually just going to be whatever acceleration we measure from the accelerometer. Well, that's where this b times ui minus 1 comes in, right? So let's look at this again. So I'll keep this at the top of the screen here, but what we can do is we can say, okay, well, we have, we already know what the acceleration is, right? We don't need to really estimate the acceleration state. And so what we're going to do is we're going to say our x matrix is actually just position and velocity. And we're going to say, I mean, you could also have acceleration as a state. Just trying to think. Well, let's leave it out. Okay, so our F matrix is going to be 2 by 2, and this is going to be pi minus 1 and vi minus 1. And in this case, how do we actually bring in the acceleration here? So this is where this comes in. This is the the input sort of equation, or the input to the state. So it's kind of like if you know what the input is. And so we're going to say plus some matrix here, and this would be, I think, a 2 by 2 times your input, and this is this would be a 2 by 1, yeah, and this would be a 1 by 1 times your input, right? And this would be times your accel, so let's say a, right? And this is actually what you're measuring, right? So this is actually measured acceleration. And so now what we can say is, well, rather than putting that into your F matrix and keeping it as a state, we already know the acceleration. And we're saying, hey, this is the exact acceleration that we need. We're just going to keep track, estimate position and velocity from that. And so remember, position was equal to pi minus 1, so that would be 1. And then plus vi minus 1 delta t, so we say delta t here. But what's at the top here? So we're saying, well, a, it's 1/2 at squared. So here we just say t squared divided by 2. Okay, and then a multiplies by this term here, and then adds to this multiplication here to give us the next position. And next is we're going to look at the velocity, right? So velocity equals the old velocity, so it doesn't include position here, so we'll say 0, but equals to the old velocity, so 1, plus this acceleration times delta t. So the delta t would go in here. Okay, so now this is our new F matrix, right? So our new F matrix is this. And this is our state at I minus 1, and this is our state now at I. So we're just going to say multiplied by, and then plus our B matrix. This is our B matrix, and then times our U matrix, right? Our U, I minus 1. Okay, and that's really it. So we're kind of saying, hey, rather than predicting and then rather than saying acceleration is constant, we're just going to say, hey, look, acceleration is whatever we measure. It's not constant. It's just whatever we're going to put in here. Even though acceleration is not an actual input to our system, we're not. I mean, you can kind of think of it as it is an input. The acceleration is being caused by the actual rocket, right? And we know the acceleration based on the measurements. So this acceleration would be, this is sort of another way of writing it. And now you have two states, just position and velocity. So you might be asking, well, how does the acceleration, if we have the acceleration in here, how do we keep track of the noise, right? Because the sensor for the acceleration is noisy, but if we don't have it as a state, we wouldn't have the R matrix for it, right? We wouldn't even have an update step for the acceleration, right? So just like I have here, update accel, we wouldn't be using that anymore because our accel would actually be coming into this prediction state, and the acceleration would be coming in down here, basically. I'll show you how to do that soon. And so but we know that the accelerometer is noisy, right? So does this just pretend that the accelerometer isn't noisy? Well, no. Like, what's going to happen is the noisy accelerometer readings will influence the velocity and position, right? And so what you're going to have is actually your process error, right? So your P matrix would be a 2x2 matrix, and then it would have some kind of noise. This is just arbitrary numbers here, but it would have some kind of noise along this diagonal that is influenced by this accelerometer, right? So you would find out what is the accelerometer noise, and then it would or let's say what is the accelerometer variance, and then these values here would be scaled by these terms here. So for example, if we want to look at this top value here, let's say this is like, okay, so let's say the variance of the accelerometer is the sigma a. So this top value, which is the one for position, would be something like sigma a divided by sigma a times delta t squared divided by 2, I think. I think it would be like that. And then here would be 0, 0, and then the velocity one would be just sigma a times delta t, right? So that's really all you would do. And so this is where the noise comes from, right? So your accelerometer noise would come into here. And you would start, I think it would just find so actually, sorry, it wouldn't be here. This is like your beginning sort of noise. You wouldn't set this to, this is more of like you set this initially for when you initialize your X matrix. I think the actual matrix here that you would set these as at the beginning, that would be constant, would be your Q matrix, right? So this is your like process noise, so how noisy you think your process is, and this is how you would set it. Let's see, yeah, and so this is sort of a 2x2 matrix, and it's, you'll see the position and velocity of the altitude. So let's just take a look at how we would write that. So up here in the Kalman filter here, first off, we would shorten these things down, right? So rather than a 3x3, we'd have a 2x2, right? So for this matrix here, the Q matrix, we say it's 2x2. Hello, Yukon, welcome. And so in this case, we'd shorten this down. So we'd say, okay, it's like this, take that out, and take this out like this. So now that's a 2x2 matrix, right? It's not easy to see, but so in this case, you would set this to some value based on the equation I showed before with the sigma a and stuff. And next is the RXL. Well, we don't have an accelerometer. We're not actually like making an update step with the accelerometer anymore. So we can just take this one out completely. For the barometer, we still have the barometer as a 1x1. We're going to use that. For the state here, it's not a 3x1 anymore. It's just a 2x1 here because of position velocity. For the P matrix, it's just a 2x2 now. So we're going to take this bottom one out and take these ones out. So it's a 2x2. For the I matrix, it's also a 2x2. So let's take these out. And this is 2x2. The H barometer matrix, this is now a 1x2 matrix, right? Because we don't have that accelerometer term anymore in the state. So this would be for position and velocity only here. We don't even need an H matrix for the accelerometer. And here for our F, we're going to say, well, that's a 2x2. We don't need a Z accelerometer here, so we take that out. We still need a Z barometer. We don't need a Z GPS at this moment, so we'll take that out. Our K Excel, we don't even have that. We're not going to have a Kalman for the accelerometer. And here for K Barrow, it's a 2x1 as well. So this is really all we need. Down here for the initialization, we would say, okay, well, remember it's a 2x1. Here again for the P, it's a 2x2. Okay, and if we go down to the predict step, here we would basically take this bottom one out. Whoops, let's take this bottom one out. We don't have this third one here, and we don't have this third one here. So remember, it's just 1 delta t, 0 and 1. And here we have f times x. But remember how before we had, or here now, we're actually including this b times u matrix, right? So the b is delta t squared over 2, and delta t, and then times this measured a. So I'm going to change this function a bit. So this predict function will actually take a float, and it'll take our accelerometer measurement, right? And so in this case, we need to say, well, x equals f times the previous x plus a a b times times a u matrix, right? So let's look at so let's just create that here. So I'm gonna just copy this just for reference. So we're gonna make a new matrix called a B matrix, and it's going to be a, let's look at it. It's going to be a 2x1 matrix here, right? So it's a 2x1, 2x1, and right now, and it's not going to be constant, right? It's based on delta t, so I'm going to be creating it down here. And we're going to make a U matrix. So I'm going to copy this again, and it'll be a 1x1, and that also won't be constant. It'll be our accelerometer measurement, right? So we got B and U. And here, let's just create B. Okay, so we say B equals, remember it was delta t squared divided by 2, and then a delta t at the bottom here, right? So we say del t times del t divided by 2, and just for clarity, we'll go down here and we'll just say times del t, or at the bottom is del t again, right? So this is, you can even just do this just to make sure that it's a float or whatever. But yeah, so there we go. So now we have our B matrix, which is in this form here. And we just need to make our U matrix, right? Which is just has the accelerometer in there. So we're just going to say U equals accel, right? Because accel was our this input here, right, from our accelerometer. And we just say, okay, B times U, and then that's it. You just add B times U in there, and that's all you need to do for the predict equation. The B times U does not come into this P matrix here. Next is, oh yeah, so now let's look at, so we wouldn't have this update accel function. So now let's look at this update barometer function, right? So the update barometer function, it basically looks the same, right? There's no change. We already changed the sizes of the matrices to the correct sizes. So the H matrix is the right size, the K matrix is the right size, and we don't need to change anything here. Here, at least, we will not, what we'll do is we won't predict in this step. So we'll take this prediction out, and we're assuming that we're doing a lot of predictions between each barometer update, right? So we're, let's say at time 0, or let's say at time, 10 milliseconds, we do a prediction, and we have an accelerometer measurement, so we do a prediction. At time 20 milliseconds, we do another prediction with the new accelerometer measurement. At time 30 milliseconds, we do an update, because our barometer has finally given us our altitude value, and we do an update. And then we do more predictions and updates. So in this case, we're not going to do a prediction step before this barometer update. And yeah, and it basically just looks the same as before. And now we're setting data variables, so now we don't have this accelerometer or accel value here, so we would just leave that out here like that, right? So this works as well. It just and really, if you have all these equations like working and it's sound, how your graph looks and how everything works is really dependent on your these values, your R value here, or your noise of your sensor, the variance of your sensor, the process noise that you think you have, and even to an extent the initial states and your initial P matrix here, and it's kind of harder to explain how to set these correctly. And it really, I guess, depends on the case-by-case basis. And even I'm not very sure exactly about how to set these. But you play around with these values and sort of, I've done just a bunch of playing around with the values and just testing and seeing what the graphs sort of show me, and see if they make sense, right? But yeah, that's another form of this Kalman filter that you can use, where the acceleration is the input. So now let's take a look at the last sort of Kalman filter I'll talk about, and this one is one that includes GPS. Okay, so we're on to the GPS section now. So and this will be more like a full example of a GPS-based Kalman filter, because we're going to not only predict position and velocity, we're also going to predict gravity, and we're going to predict the barometer bias. So we're going to be tracking without us caring, like, without us. So the previous examples I have shown, they all rely on the fact that A, you have zeroed out the acceleration, right? So if your rocket is sitting on the pad and it's not moving, the acceleration is showing up as 0, right? So it shouldn't show up as negative 9.81. You should bias that. You should take that bias out, and it should be close to 0. And we're also assuming that your barometer bias is also zeroed out. So your barometer is fluctuating around 0 as well if it's just standing still. But what if you don't know the gravity and don't know the bias of your barometer, and then like how do you track this stuff? And also, like, you can do this by including a GPS, which will provide you more like an absolute sort of measure of the acceleration without biases. I wouldn't say without biases. I guess like if you're like above sea level, you'd have a bias altitude. But anyway, so let's just look at an example of how you do that. So we're gonna go to a new one of these, and we're gonna make a new state matrix, right? So let's look at new. So remember, our X matrix is going to look like this. So our states are going to be position, velocity, gravity, and bias. Okay, so we're going to say position, velocity, gravity, and bias. And this is barometer bias, okay? So this is barometer bias, okay? And so now, this is when it gets kind of interesting. So let me just remember how this was done. Yeah, okay. So this uses 3 sensors, right? So this uses an accelerometer, a barometer, and a GPS, right? And it uses the altitude from a GPS. And so how do we like? So first, let's create this prediction sort of function, right? So let's find F, let's find U and B and stuff like that, right? So we're gonna say, is gravity our accelerometer bias in this example? Yep, that is correct. So gravity, if this is only if like the accelerometer is, I guess, is not zeroed out. I think even if you zero out the accelerometer and there's still a little bit of bias, like 0.2 or something, even 1, this will still track it. So it doesn't matter what your bias is, but it'll still track it, I think. Don't quote me on that. I think this is only valid if it's like gravity, because gravity will affect the speed of things. But yeah, gravity is the accelerometer bias in that case, right? But really it's the bias due to gravity, right? Not due to, due to gravity, let's say, right? And the reason you might want to track it is like if you're on some, like if your accelerometer maybe is wrong a little bit, or like you're in a different part of the world where like gravity is slightly different, which is the case in a bunch of places. But yeah, so that's sort of the state, and we're going to say that state equals an F matrix, and this is going to be a 4x4 matrix. Oops. Okay, that equals some F matrix times our PVGB matrix, the previous values, plus our BUK matrix, right? So B would be like this. Let's just say this is X and this is X and this is B, and then times our Excel value, right? Accelerometer, or let's say, yeah, Excel measurement. I mean, they naturally change their bias when the package heats up and stuff. Yeah, so they naturally change their bias when it heats up. I'm not 100% I think like this tracks that bias too. And I'm not exactly sure if it would be a problem, like, because the thing is, like, I think it checks gravity based on the position velocity and stuff like that, and acceleration, but I'm not sure if it just simply looks at the bias or if it actually is like trying to detect gravity and it just so happens to be the same thing your accelerometer bias is. So I'm not 100% sure. But yeah, so now we just need to find out, well, what is the position based on all of these terms and the acceleration, right? So first off, so let's just write this. So pi equals pi minus 1 plus v delta t like before. What about gravity? Well, gravity would be, it would be minus, so this gravity's pulling it down, right? So we're saying minus g delta t squared divided by 2, and then plus excel, the actual acceleration, delta t squared divided by 2. Okay? And then we're saying, then next is velocity I, and that equals vi minus 1 plus excel delta t squared divided by 2, basically, right? Oh, sorry. And then minus g delta, whoops, excel delta t minus g delta t, like that, right? And then our gravity, we're assuming our gravity is going to be constant, so we're going to say gi equals gi minus 1. And we're saying our bias is also, we're assuming also our bias is going to be constant. That's just our best guess, at least for equations. So bi equals bi minus 1, something like that. So how do we, so now we just need to convert these into our F matrix, right? So, or our F and B matrices. So our F matrix would be pi minus 1, so that would be 1. What about velocity? Well, that would be delta t. And then here we can, what about gravity? Well, it's just negative delta t squared over 2, right? So negative delta t squared over 2. And bias, our bias doesn't have an effect on position in this case, so we say it's 0. Next is velocity. So we say that position doesn't come into effect here. Our velocity from before does, so we say 1. Usually, so remember, usually 1s are on the diagonal here. And next is gravity again, so we say negative gt here, and then bias doesn't come into effect with velocity either. Next is gravity, so we say position doesn't come into effect, velocity doesn't come into effect, but we're saying gravity is constant, so it's just 1, and bias doesn't change gravity. And here, the same thing, 0, 0, 0, and bias, we're saying bias is constant. So that is our F matrix here. Next is, what about a B matrix? So remember, here we have acceleration terms, right? So our acceleration here is delta t squared over 2. So delta t squared over 2. And here it's just delta t for the velocity. And for gravity, it doesn't affect gravity, right? So how much we accelerate doesn't actually affect what gravity is, so we say 0. And it also doesn't affect the bias, right? So we say 0. And there we go. So we have our F and B matrices here. So now what we can do is, let's write this out here, right? So I'm going to see, let's try to make this half and half. Yeah. Okay, so let's write the F matrix. So our F matrix is going to be 4 by 4, right? So F is a 4 by 4. I'm going to just change the sizes of all these matrices right now real quick. So the Q matrix is going to be 4 by 4. Let's just put in some values here. So 0, 0 here. Oops. This would be 0. Let's just put 1s on the diagonal here for now. right? So 0 here, 1 here, 1 here, 0 here. Okay, so this is a 4 by 4. This R barometer is still here. What we need is we're going to need an R for the GPS as well. So let's go R, call it GPS, and whatever, call it, sure, there can be something like that. It's still a 1 by 1 because the measurement is just a single value. Next is we have our X value. And so, so one thing is like, the reason is why we have this R matrix as 1 by 1 is because we're doing the update steps separately, right? So our GPS data comes in at a different time than our barometer data, right? So I know from my barometer, it comes in at about, I guess, every 20 milliseconds, 30 milliseconds or something. But the GPS value for me comes in every second. So we don't want the Kalman filter to wait for the GPS in order to update with the barometer and the GPS, right? We don't want to go as slow as the GPS does. We want the barometer to update the Kalman filter anytime it can, and the GPS to update the Kalman filter whenever it can. And so that's why we split these apart into separate sort of measurements. You might see sometimes a R matrix is not 1 by 1, but it's like 2 by 2 or something, right? There's multiple elements in here, and that's because the Z matrix would also be multiple elements, and that would be like if you would do that if you were to wait for the GPS to come in before you update the barometer as well. So it's kind of like you're putting both measurements at once into one update step. And so your R matrix would be, a 2 by 2 matrix. Your Z matrix would be a 2 by 1 matrix, right? So it would be both your measurements in the Z matrix. And a few other, your H matrix would be like your H matrix would be corresponding to that as well. But usually, because we don't have measurements coming in all at the same time, we split these up into separate update steps. So there's the R matrices. Here, this would be a 4 by 1. The state would be a 4 by 1, so 0, 0. And also, you can initialize this X matrix to whatever you think it's going to be from the get-go. So we're pretty sure that the gravity bias will be negative 9.81 or something, right? And you can even look at your barometer bias and try to figure that out, and and then say, let's say the barometer bias is negative 50, right? So it starts out at negative 50 meters for some reason. But you can also just say it's 0 right now, and we're going to add some noise to the P term here, just to say like to say how uncertain we are in these values. So the P matrix here is going to be a 4 by 4 as well. And so we're going to say, this is, let's say 0, 0. And this is also going to be a diagonal matrix here. So we're just going to fill out these terms here. And make it a diagonal. Okay, so in this case you'd say, okay, well, how sure are we that the position is 0? Well, you could set this from like your first GPS measurement. So at the beginning of your Kalman filter, you can say, well, my position is whatever my GPS is telling me. So if your GPS is saying you're at 5 meters, you would put this as 5 meters and say, you can say how sure you are and say, maybe put a 10 here. And the same thing here. You can see this one is kind of a little bit more tricky because like you don't really know what the measurement, like the velocity measurements what the measurements will give you for velocity, or what it'll predict, but you could put that as 0 if you're standing still. And then here it's like, how sure are we that it's negative 9.81? Could it be negative 9.7 or something like that? Then then you could adjust this number accordingly. And then for the bias, we're not sure that the bias is anywhere near to 0, so you can say this is as 100 or something like that. And again, these values here are really just kind of arbitrary. They're not, this isn't like a rigorous mathematical way of setting these values properly, and you can Google on how to set those properly with equations and stuff. The I matrix would be a 4 by 4. and this would just be the identity matrix. So I'm just going to copy this and just set these to 1s here, like that. Okay. Your H matrix for the barometer would be a 1 by 4 matrix here, right? So 1 by 4, and this would be 0 as well, because the barometer. Oh, actually, so I'll show you how to get the H matrix. So right now it's not actually 1 0 0 0, but I'll show you soon. You'll have a H matrix for the GPS. So we're going to say H GPS. And that'll also be sort of the same size. We have a 4 by 4 F matrix, and we have Z and K matrices, but for the GPS here as well. So GPS, and the K would be a 4 by 1 here. The Z would be a 1 by 1. There we go. So that's how it would look. We're going to also make a function down here. So this init Kalman, I'll come back to this. For now, we don't need it right now because we're going to initialize. We can initialize at the beginning. But for the let's see, for the update barometer. So updating barometer, we don't need to do anything special here. So that's the kind of cool thing, is we don't need to do anything special. We're just going to make a new function here that is based on the GPS. So we're going to actually update GPS here, right? So we're going to say update GPS, and this is going to be GPS altitude. And we're going to set that to this matrix. So rather than Z barrow, H barrow, all those things, we're going to say, I'm going to just do a replace here. So anytime I see Z barrow, I'm going to say Z GPS, and I'm just going to do it for inside this function here. There, I'm not going to go up there. Okay. Next is every time I see an H barrow, it's going to be an H GPS, and I'm going to start it here. 1, 2, 3, 4, 5, 6. Okay. And every time I see a R barrow, I'm just going to go I'm just going to type this in GPS. R barrow GPS here. That's really all it needs. And then every time I see a K barrow, I need K GPS, right? So switch that around, boom, boom, boom. Okay. So there's no barrows anywhere here anymore. It's just all the GPS stuff. Yeah, so this is our update GPS function and our update barometer function. Let's go back to this F here. So let's set this F to the actual F that we created here. So let's move this here, and this is going to be 1 del T, and then here negative del T, but it's del T squared, so we need to do negative del T times del T, like this, divided by 2.0. And then there's a 0 here. And then this velocity is 0, 1, and then negative del T, 0. And then gravity is 0, 0, 1, 0. And bias is 0, 0, 0, 1. Okay, there we go. Next is our B, and it looks like our B is the same as before, right? So our B term, our B term is the same, right? Del T squared, and then del T. Oh, sorry. So it's actually a 4 by 1. So we're going to say 0, 0, something like that, right? And our Excel is still our Excel. So it's still our U value here. And this equation is still the same here. So that is it, I think, for that. So now let's look at how do we find these H values, right? So this is where it's important. So for the H values, so let's look at this section again. So the H values, remember that we said that Z, our Z must equal H times our X, right? And so we're going to say Z, for this case, Z barometer, let's look at the barometer. Z barometer equals an H matrix, which will be like this, times our X matrix, right? Times P, V, G, B. Okay? And so let's look at, how does the position and bias relate to the measurement? Well, we know that the measurement that we get from the barometer, right? It's equal to, the reason it gives us this measurement, right? If it says 100 meters, the reason it gave us 100 meters is because we are at some height, right? So P, plus we're at some bias, right? Plus some bias. So height plus bias gives you your measurement, right? So we can even say, you can sort of think of this way as well, like our actual position equals whatever we measured minus our bias, right? And that's true, right? So whatever we measured minus our bias is our actual position above 0, right? So in this case, we can say, okay, well, z barrow equals p plus b. So, and also remember, z barrow has velocity and gravity has no influence on what we read with the barometer. So it's just a function of p and b. So we say, okay, well, there's 1 here, right? Velocity and gravity, that'll be 0, 0, and then barometer here is 1. And this is where the whole this is where bias actually gets like taken out, right? Like this is the whole thing where bias is, the Kalman filter is like, oh, okay, that's how I get the bias, and based on the magic of the Kalman filter, I'll figure out the bias using sort of this knowledge of how the bias influences my measurement. And then it'll also say, I'll figure out the velocity and gravity and position without the bias, because in this predict step, we have the bias doesn't influence those things. And so this is our H for our Z barometer, right? And as far as GPS, it looks the same as the last time, right? So Z GPS looks the same, is basically the H matrix for GPS would be 1, 0, 0, 0, right? So that would be P, V, G, B. Because the H matrix, because only the position, the only thing the GPS, at least as far as we know, the only thing that influences the GPS is a position. You can even, like, it's kind of like, you can also think of like the states of, you know, like the GPS is not only going to be influenced by position, but it might be influenced by like your signal strength or like how accurate your GPS is and stuff. But like none of these the other 3 variables here don't influence what the GPS will read, right? So only the position, as far as we know here, is changing the measurement, right? So in this case, the H would be 1 here like this. So let's go back to this code here, and we'll say H barometer has a 1 over here, right, at the end, and the GPS has a 1 over here, right? And that, I think in this case we're done here. Yeah, we have our B and U, we have all that, and we have our update barrow and update GPS. So let's just look at, and obviously we'd have our, you know, update. You need to define those functions here. So update GPS, update barrow. You wouldn't have update Excel in this case. You would have predict, and you would say that takes a float Excel, right? And I guess let's just run through a quick example of kind of how you'd use this, right? So let's make a new file, and let's say, or actually let's just do this here at the bottom, right? So let's say you're in your main. Okay, let's just make this. Let's do main.cpp. Okay, so you're in your main, and you have your void setup. You know, you say, and then you say, you know, you do things like init accelerometer, and then init barometer, and then init GPS, things like that, you know. And you'd have, you know, you would include your Kalman.h in here. And in this case, let's say, because we don't have this as a class, right? So this isn't really a class, it's just, we only have one Kalman filter, and this is it. We are just going to, you would say, okay, well, let's say in the Kalman filter here, we don't need to initialize it, essentially, because at the very beginning, we're already saying our x values are these, and our p values are these, so it's already kind of initialized at the very beginning of your program. And so we don't need to do that. And one thing that you could do is, I use this library called Chrono, and that just helps with timing and stuff. So if I do include Chrono, let's say, and you'll see how that works, because it's pretty intuitive. and so I would say if I want to make a timer, right, and I want to do something every 10 milliseconds, then I would say, okay, chrono equals, let's say this is a Excel timer, right? And we're also going to have a chrono GPS timer, for example. And we have a chrono, barometer timer. Okay, so that sets those up. And then in our loop, assuming you have the GPS, barometer, accelerometer all set up and giving you measurements, in our loop you can then say, okay, if Excel timer dot has passed, let's say we want to do this every 10 milliseconds, right? So we know the accelerometer gives us. Oh, sorry. So we would be saying, okay, let's say we would say get Excel, right? So we're getting acceleration. Or actually, let's just do this. Let's say if Excel timer has passed 10 milliseconds, we're going to, from that Kalman filter, we're going to say predict, and we're going to say, we're going to put the acceleration in there, right? So you can say, hey, Excel equals get Excel, right? And then you would just put Excel into the predict step, right? And then under here, you would have to write Excel timer dot restart. So it just restarts it and gets ready for the next time, right? So this will only run if it has passed 10 milliseconds, right? So it kind of does it non-blocking. Here we can do another one. If GPS timer dot has passed 1,000 milliseconds, right? So a second. We're going to say update GPS with, let's say we have a variable called GPS altitude. Update GPS with, get GPS, something like that. And we're going to update the GPS with that altitude. And we're just going to say GPS timer dot restart. And we just need to restart it, basically. Lastly, we say if barometer timer, how do we do it? Barometer timer dot has passed, every 30 milliseconds, we can say float barometer equals get barometer, and we're going to say update baro of barometer, and then we're going to say barometer timer dot restart, something like that. Okay, and so, whenever you need the latest data, you can say, maybe after each loop or something, right? But maybe not. You'd say, whenever you can say, hey, we can say float position equals, it would be, I guess, get position, right? Like it would be get common position. And it would give you the position, and then if you need the velocity, you would get common velocity. You would have to extend these functions, so you would have to go down here and say, okay, well, rather than only getting position, we also are going to get, velocity. So this would not be 0, 1. This would be a 1, or 1. This would be 1, 0 here. You can do get gravity, and this would be a 2 here, and then bias would be something like this. This would be a 3 here, right? And then you would obviously put these into your header file as well, make sure to find them, and then you would use them down here whenever you need it. So this timer is really just an example of how, just to show hey, you can get these measurements every 10 milliseconds or, at various times, and they would update these things by themselves. But rather than this probably happening, what you would probably do is more you would have something that is checking your accelerometer each time, right? Or let's say, you have something that is, for the accelerometer, this is probably pretty accurate to what happens. Or you can have something that is, it's probably what happens. But here, rather than GPS timer dot has passed, you would probably be have a function that non-blocking checks if there's any new GPS data. And if there is, then update the GPS with that data. And the same thing with the barometer. It would check, is there new barometer data? And if there is, get the data and put in the update barometer, right? So you wouldn't necessarily have timers here for each of these things. It might just be checking when things have sort of happened. And I think you would usually want your predict step to happen faster than your timer and barometer timer step, right? So this is why like the accelerometer timer is every 10 milliseconds. You want to have a bunch of predictions. So what's going to happen is your program is going to be like this. It'll do predict. It would do predict, and then at some point it's going to say update barometer, and then it's go predict again, update barometer, and then at some point it's going to say, you know, predict, update barometer, and then update GPS, and then it'll continue doing update barometer, and then it'll do update GPS again, right? So what's happening here is as it does tons of predictions just based on the previous state and the acceleration, it sort of loses its accuracy, right? It drifts, and then barometer comes in. It says, no, you drifted too far. This is what it actually is, and then you start predicting from that point, and then it says, no, you drifted too far. This is the next one, and then it drifts from that point, and then the GPS comes in, and because the barometer has a bias, the GPS comes in and says, no, you both have drifted too far. Sort of, and like, you know, this is your bias barometer. Remember what you know, I can tell you what your bias is because I don't have a bias, and then the GPS sort of fixes that. But the GPS fixes that, you know, every 1 second in this case, right? It's much less often. And actually, if you plot your, let's take a look at just some graphs real quick. So this is a graph from the Discord that I posted. If we look at, this is sort of my graph of the GPS, my GPS data. So this is my recent GPS data that I got. And here I have a world accelerometer value. So one other thing is, remember that the acceleration needs to be in your world coordinates, right? And not your rocket coordinates, right? So you want to make sure that if your rocket rotates and it's still going upwards, you're tracking the upwards velocity, not the sideways accelerations, right? So you, out of the scope of this video, we're saying we already know how to rotate the acceleration based on the gyros and stuff, based on the orientation of the rocket, so that we're always only getting the acceleration that is upwards. Yeah, you can ask about that, I guess, in the Discord or something like that if you need help with that. But it's a bunch of quaternion stuff. But so here you can see this is my measured world acceleration. So this is what I put into the Excel, my U matrix basically, right? And you see here it's almost 9.81. It's a bit less. And here is my position over time. So it says it's at like 9 or so or 10 meters. You can see here my velocity is, you know, it's sort of in the middle at 0. And then gravity, you can see here it's estimated gravity pretty well. So, you know, gravity is about 9.75, 9.76, and that looks about right here as well, right? So the middle point when it's not moving is about 9.7 something, right? At the same time, the barometer is here. So the barometer is like negative 61 or something. And the barometer bias here is about 71. So I think there's something, yeah, it just has taken a while. It takes a while to settle on the correct value because my GPS isn't that great, and I was doing this indoors, so the GPS was like bouncing up and down a bunch. But you can sort of see here on the GPS readout, it gives like stepped responses, right? So every second it steps and it gives you it gives the value, and you can see down here is my P matrix, the values of my P matrix, so the position and the velocity. And so you can see what's happening is, as time goes by, the uncertainty gets higher and higher and higher of my position until the GPS comes in at every second, and it brings the uncertainty down, right? Because the GPS tells me, no, your actual position is this. And then as we keep predicting and updating with the barometer and stuff, the position, the uncertainty keeps rising, and the GPS comes in and says, no, this is the actual position. And the same thing happens with the velocity. As the velocity readings get more and more uncertain until the GPS comes in and we settle down at a lower value right here. You can see here as well, we also have our gravity p-value and our bias p-value. So our gravity starts to become more and more uncertain until the GPS comes in and it brings it down to make it more certain, right? And same thing with the bias of the barometer. So this is what you would expect in your Kalman filter in this case. This Kalman filter needs more tuning, so I need to properly tune the right values for the Q matrix, so the noise matrix, and the R matrices and stuff. But yeah, so this is sort of what it looks like sort of at the end. If you want to, let's see, if you want to know more about Kalman filters, this is a great resource right here. This is a really good website about them, and particularly the multidimensional Kalman filter here. There's also like a bunch like more easier stuff. So this actually tells you about like things like variance and normal distributions, and how that sort of works with the Kalman filter. So this is a bit more than much more than I've talked about today. So it's really good. There's also this resource here, this Kalman filter in pictures, which talks more about the variance and sort of gives you a better intuitive feel of what variance means and how it changes over time, and sort of how the prediction and update steps work. So this is a really good resource. Just remember that last equation here, the one that gets the P matrix, this one here, don't use this one because it's numerically unstable. Use the other one, the longer one. And you can sort of see here a little diagram of how this works, right? So you get an initial prediction of where you are, right, your state and your P matrix, and you combine those with your F matrix, your B matrix, and your U matrix, plus your noise matrix down here, and you get your new predicted state and your new predicted P. Then you go into your update state whenever you get a new measurement, and then you combine your H matrix, your R matrix, your Z matrix to basically get all these equations, right? And then you get a new state, your new estimated state. And then you bring that estimated state into the next predict step. So this happens again. So it sort of continuously happens, right? This predict step could actually, if you don't have an update ready and you want to predict faster, you can actually get the output of the prediction, bring it back into the input of the next prediction. And every time you do have an update step, do the update first, like do the update. And so it doesn't have to be always in this sequence. Another good resource is Amazon.com. So there's a book by Paul Zarkan that is called, he writes about tactical and strategic missile guidance, but we're looking at fundamentals of Kalman filtering. So this is a good book that sort of talks about these things, and he's got a lot of examples in Fortran, which go way over my head, but they're very. He goes through like all like the derivation of a lot of the examples, and it's really cool because like there's like I think one of the really cool, really good examples in here are like a falling projectile, where it looks at like tracking with a radar, like looking upwards, a falling projectile with gravity and drag on it, and predicting what the drag coefficient is on it based on how fast it falls. So this is really useful. Probably a lot of these other books, like there's optimal state estimation. This is, I think, the one that Joey B recommended in his videos. And there's more stuff here that's like nonlinear Kalman filtering and unscented Kalman filtering and extended Kalman filtering. And so this is probably another good resource. I don't think I've read this one. Another thing that's important is to know that like a Kalman filter, like this regular standard Kalman filter, really only works on linear equations, right? So if your system is linear, or if you're trying to predict a linear system, it will work fine. But usually in real life, nothing is linear. There's a lot of stuff is nonlinear, and so a linear Kalman filter will work probably okay in a lot of situations, and if you have enough process noise in it, it might work okay, but there's also a lot of times where it won't, and that's where like an extended Kalman filter comes in. And with an extended Kalman filter, it's kind of the same steps, but rather than having a linear equation with like your F matrix where things are like linear and stuff, you kind of figure out, it's kind of like you figure out the derivatives of the equations, and I don't really know exactly how this works, but you figure out the derivatives of the equations and you put them into your Kalman filter, and it sort of works in that way. There's actually a good YouTube video on it. Is it this one? Yeah, so this one's a good one. Kalman filter and EKF. This guy is really knowledgeable and explains it really well. But he kind of goes a bit more into the math. And he talks about the extended Kalman filter. A good one with the extended Kalman filter, I mean this is good too probably, is this is the one I liked, or this one? It's the one in MATLAB, so it's by, oh not this one, it's this one with the cool graphics. So it's sort of, yeah, this is the good one. So it's basically saying how, you need, with an extended Kalman filter, you need to sort of do it a different way, and sort of shows the intuition on how it works. This kind of made it click for me a much more than what I knew before. This also is a good tutorial. This sort of tells you how to do it in Simulink in MATLAB, and this is like the official MATLAB channel, and this is really good too. Yeah, and I think that looks like that's it for all I really wanted to say today. I guess I don't think this code is ready yet. I'm going to maybe paste it in the Discord channel, or maybe I'll just paste this code in GitHub and then put it onto the description of this video. Okay? Yeah. Anyway, so thanks for watching. That was kind of cool. It was sort of my first chat, I guess, or my first live YouTube thing with people watching. So thanks for that. And yeah, if you need help with anything, and let me know in the Discord channel. Maybe go onto the control theory channel and just like ping me to those. Because if you do a private message, then others won't be able to learn from that. Yeah, and thanks for watching again, and see you guys next time. Probably I'll be doing a launch probably sometime soon, so I'll make a video on that or something. Anyways, cheers.